So for Unit 2, we're going to still be in the realm of descriptive analytics, but now we're moving on to visualization, pretty much plotting, graphing, those sorts of things. So we saw a little bit of this at the end of Unit 1, where we had looking at relationships, possible relationships between two variables. So now we're going to get into more detail on the visualizations and different plotting techniques. So why do we plot the data? Well, humans enjoy attempting to look for pattern recognition. So they love to do this, and we're actually quite good at it. It's actually innate from us in the fight or flight kind of stuff, and we're good at noticing patterns. Sometimes we're almost too good at it, where we see a pattern when one really does not exist. So what we're going to do is we're going to plot the data and try to find patterns. So again, many times we're interested in relationships or associations between two variables. Sometimes it might be between more than two variables, but right now we're going to restrict ourselves to two variables so that we can plot in two dimensions, an x-axis and a y-axis. So a scatter plot works really well for this type of analysis, like we saw at the end of Unit 1. Right? So let's take a look at several different sets of data. This is called Anscombe's quartet, and I have the source a little bit later. I'll tell you where I got the data from. And there are 4 different data sets, hence the quartet: 1, 2, 3, and 4, and then Roman numerals at the top. They each have an x and a y, and the x and y's are paired. So if we look at the data in tabular format, like in a spreadsheet, then there's not a whole lot that kind of sticks out to us, I don't think. I think the biggest thing that might kind of stick out is in data set 4. We see all of the x's are 8s except for one of them is a 19. So data set 4 looks like it might be somewhat crazy looking, but everything else, you know, it's kind of hard to tell in tabular format what things look like. So what we learned from Unit 1 was come up with a bunch of different summary statistics and see what happens. So if we do summary statistics, we take the average, the mean, of each x variable is 9. The average, or mean, for each y variable is 7.5. The sample variance for x for every single data set is 11. Sample variance for y is 4.12. The correlation between x and y is 0.816. And the best fit ordinary least squares line is y is equal to 3 plus 0.5x. So what does that tell us? Actually, not a whole lot. It makes it sound like the data sets are all the same. So let me back out of this for a second and go get the data set and compute these to show you how I came up with that. All right, so if we go to this guy, under Materials, Unit 2, Anscombe's quartet. All right, and then it downloads, and then I should be able to open it in Excel. All right, so I need to do, let's see, I want the mean, and maybe let's make this a bit bigger, which would be average of all of these guys, all the x's. All right, so 9, right? And we said that was the same for all of the x's. So I'm just going to drag this across. So it's 9, 9, 9, and then 7.5. Right, this one's exactly 7.5. These go a little bit further out. So we did that, and what else did we need? Sample variance and then correlation. Sample variance. Remember that is var.s. The S stands for sample. And again, we take those data points and get rid of the extra E. And I should be able to drag this guy over. 11, 11, 11, 11, and then 4.12, 4.12, 4.12, 4.12. So, you know, rounded to 2 digits, that's all the same. So, very, very similar. And then we said the correlation coefficient between x and y is correl. Put the x's in, comma, the y's, 0.816, and this one I'm going to copy to there. Make sure it did what I wanted it to do. Yes, yes, yes. All right, so the correlation between the x's and y's is 0.816 for all of them. And then the best fit OLS line, ordinarily squares, we need an intercept and a slope. So the intercept we can get with intercept. The known y's, make sure you get the correct order here, comma, the known x's. And we see 3. And then this one, and this one. Just check one of them, make sure. Looks like it's working. And then slope is the slope of the line, the best fit line. Again, it's known y's as the first parameter, and the second parameter is an array of the known x's. 0.5, and then should be able to copy that over. That's on exactly 0.5, slightly under. Right? So we see that the best fit line is y is equal to 3 plus a 0.5 times x for all 4 data sets. Okay, so again, looking at this, it looks like it's halfway fine. So what do we need to do? Let's plot each one. So to do that, we're going to do a scatter plot. So let me plot this first one. I'm going to select those guys and go to Insert, Scatter, and that looks like it's doing about what I want it to do. Right? And so I'm going to, let's move it over to here. Right? And do we have anything that's less than 4? No. In the y columns, doesn't look like there's a 3 right there, so might not want to do that. So let's make it pretty. The chart title here is data set 1, and I don't like grid lines for scatter plots necessarily, so I'll get rid of those. And then I like rounded corners, and I'm going to go ahead and change the scale of this slightly. So I'm going to format the axis, and I'm going to do a minimum of 3 and a maximum of 15, right? And let's leave it like that. So looking at this, right, it looks like there is some kind of linear trend going up at about half a unit, right? And the data kind of fall around what looks like an upward linear trend, which is what we would expect from perhaps that intercept and slope equation out here. Now I'm gonna go Control C, come down here, paste. I'm gonna do that 3 times, and then what I'm gonna do is I'm gonna change where it's pointed to for each one. So this is data set 2, and then go to select data, and I'm going to edit, and the x values are now in data set 2. The y values are now over here. Click OK. Click OK. And when we do that, we immediately notice, that's not what we were thinking, or that's an interesting pattern, right? It goes up, it's curvilinear, it goes up, and then it starts to drop down, right? And then let's go ahead and do data set 3. Close that, and then actually if I click on the data, I ought to be able to just drag it over from up here, right? And then let's see what it looks like. So data set 3 looks like a very straight kind of line, and then boop, one way up there. Right? And then data set 4 and then let's get rid of this and let's drag it over like we did the first time. I think it's a little bit faster. All right, the Y's, the X's. And then let's go down and look. Let's see what it looks like. Remember, these were all at 8, right? And then that guy way out at 19. All right, so the scale on this one's slightly different. It's 19 out here. All right. So looking at just the tabular format over here, and even calculating to summary statistics, you would think that all the data sets are similar. However, when you plot the data, data set 1 is probably what you were kind of expecting. It's I'm going to add a trend line here. Linear. I want the display the equation on chart, R squared on chart, and then I'll move it over to here. All right, so that gives us the slope and the intercept, and the R squared tells us how good of a fit that line is. So it explains 66% of the variation in the Y based off of the X's. So this is kind of what we would expect, and most people kind of expect, because that's what they've been taught to understand when they see descriptive statistics. All right, we have some kind of middle line going on and things falling kind of somewhat randomly, about the same above, about the same below. This one, on the other hand, so again, we can add a trend line. We'll do linear. We'll do this and this. All right. Notice that, you know, we get the same equation, and we also get a very similar R squared value. But the R squared doesn't tell us everything we need to know, because we see very different things going on here. All right, so for this might almost look kind of like a product life cycle, kind of. You know, it builds up, kind of gets to maturity, and then starts to taper off. Right? This data set, also on the other hand, right? Let's add a trend line, linear, all that fun stuff. Again, the R squared's very high. That's the correlation coefficient, right? Is squared. But notice that we have something here that is certainly an outlier. It doesn't match the pattern. So for that, we'd be concerned and want to do something else. And then this guy, let's add its trend line. And we display these guys. Close it. And again, right, we're getting high R squareds even though there's something really going on. Right? We have a bunch of things where X is always 8. And we all are grouped up. And then one that's out here that's pulling us up. So again, this does not fit the pattern, so something is going on. So by being able to plot the data, we can recognize different patterns. This is kind of the regular / quote normal pattern, where things kind of fall randomly about a straight line. This one, we definitely have some kind of curved linear stuff going on, a pattern that the linear is not going to be good enough. We should fit a polynomial to this instead. We could do that. Let's do that. Add a trend line. Let's try polynomial of 2. All right. And boom. So that's the polynomial. Perfect fit. R squared equals 1. So it tells me this is how the NSCOM generated that data. Okay. This one, I would want to exclude this outlier and look at these guys. What I would do is, in reality, I'd see what this is and why it's doing it and try to fix it. Or if it's a good thing, I'd try to incorporate it to the other stuff. And this one over here, again, I'd try to figure out why this guy is way out here and what it's doing and why is it causing me to be pulled up that way. So plotting the data is helps us understand stuff better than just looking at summary statistics. So here I've got them all nice in one big plot. Looks like I was actually smarter when I made this. I did everything out to 20. All right, so we're on the same scale at 0 to 20. I should have done 3 to 20, but oh well. Right. So the source of this data was developed by Francis Anscombe in 1973. It was Graphs and Statistical Analysis in the American Statistician, Volume 27, Issue 1, pages 17 through 21. And it's now used as a reason, showing a motivation as to why we should plot stuff. So that's to help hopefully make you understand that we should plot things, not just look at summary statistics.